Hello and welcome to my math YouTube channel. My name is Seth Lowe and I'm going to be working out of the Proofs and Fundamentals book, a first course in abstract mathematics. This is a very old edition. I've been out of college for a while. I play a lot of video games in my spare time. And recently, I play a lot of video games in my spare time, and recently it started to feel kind of like a waste of time. I enjoy it, and I want to play them some, but I feel like I should do more than just play video games. Anyways, let's go ahead and get into it. I want to go ahead and start in Chapter 2. And the reason for this is because Chapter 1 is all about logic. It's really basic. If you're in college and you're taking a proofs class right now, I don't think you're going to have too much trouble with the first little bit. It's about statements, how to make statements. Basically, it's foundational work for how you're going to do proofs. And just showing that it checks out, saying that you can prove stuff through contrapositive, saying that if the conclusion is false, and then you can prove that the hypothesis is false, then the overall statement was true. And you go into the logic of how all that works. But as far as actually solving proofs, I don't think it's completely necessary. So I want to go ahead and jump in. And if you would like to see me go over the some of the stuff in the logic section in Chapter 1, leave a comment. You know, if enough people want me to do it, then I'll go back and I'll actually go ahead and do that. So we are going to start in 2.2, and here we go. Our first exercise is 2.2.1. It says, outline the strategy for a direct proof of each of the following statements. Do not prove them because the terms are meaningless. So this is a good one to start with, I think. The first one here says, let n be an integer. If 7 divides n, then n is bulbous. So calling n bulbous, that's the meaningless term. However, 7 divides n. That is a real legitimate term. So if we were going to try to prove this, the whole section is about direct proofs. So we would need to try to prove this directly, saying that taking the information that we're given and trying to arrive to the conclusion. And the most important thing, I think, really with any mathematics that you do, it's your definitions. You have to understand how things are defined to be able to use that system that you're learning. So if you are struggling in a math class, try to get down to the definitions first. If you have those definitions memorized and you truly understand what they mean, it'll make a world of difference. Then the exercises, they can still be challenging, but without an understanding of the definitions, we can't get anywhere. So let's see, this first one, it said, let me readjust this. Okay, so it said, let n be an integer. Okay, so we automatically, we're saying if 7 divides n, then n is bulbous. So I guess the way this proof would work would be, let n be an integer. Then we're going to say, suppose 7 divides n. Now, how we would move further in this is we have to know what this actually gets us. What does it mean for 7 to divide n? Honestly, I haven't looked at my book in probably about 10 years, so I don't know. And the definition, it says, let a and b be integers. the number A divides the number B if there is some integer q such that AQ is equal to B. So A divides B, we would write it A horizontal slash B. So we know that if a number divides another number, then the number that divides that other number has another integer that we can multiply by that number to get the other number. Sounds complicated, let's write it down. So basically, that little refresher helped a lot. Let's say you have two integers, A and B. A divides B if there's an integer Q such that B equals AQ. Just like that. Just simple as that. So now that we know what that means, we're going to say, so we suppose that 7 divides in, then there must exist some integer, we'll call it Q, just like in the definition. We'll just say there's some integer Q out there such that n equals 7q. And that's as far as we're going to be able to get in our first example. So it says from there we would assume n is bulbous. Obviously, n is n being bulbous. It's a meaningless term. So, assuming it was a real term, we would have a definition for what bulbous was, and we would show that from this definition we met the requirements of being bulbous. And that would be how we would prove that first one. Let's go ahead and move on. We'll go to number 2. Number 2 says every globular integer is even. So let's go ahead and write that one down. It says every globular integer is even. So from here, let's see. You've got to show it for every single globular integer. So in this example, we would start with a globular integer. So we would say pick some element, we'll just say some element n that exists inside the set of integers that is globular. And then we could say, since n is globular, we get such and such, whatever globular may mean. But we would have a definition for globular. We could expand on that. And to prove that an integer is even, we have to prove that it is 2k 2 times some integer. So k inside the integers. This is what we need to be even. So that's as far as we could go there. We would just say we want to pick some random integer, and we want it to be globular. But we don't care which globular integer it is, because we want to prove for every globular integer that they're even. So that's why we're just picking some arbitrary integer here. That's why we just said pick some in. Doesn't matter which one as long as it's globular. And then from there we can just say, okay, globular integers do this, which by definition leads us to 2k such and such. So let's go ahead and get into some of the actual proofs. So this next one says it's exercise 2.2.2. And we are given, it says let n and m be integers. And we are going to suppose this for all three exercises on 2.2.2. It says the first one is prove that 1 divides n. That 1 divides n. Now, if you remember from the previous example, or from the previous exercise, we went over what it meant for a number to divide another number. So if you're paying attention there, you'll know that if 1 divides n, then there exists some integer such that n equals 1 times a. We'll just say there's some integer a such that n is 1 times a. So, how could we prove that? We know n is an integer. Well, 1 is an identity, so we know that anything that we multiply by 1, we get that number. So, really, the only thing we need to show here is that all we really need to do is say n is equal to 1 times n. So that one's very straightforward with the definition. We're going to move on to the next one. Like I said, all we're doing here is we're just saying, we know that there's some integer such that n is equal to 1 times that integer. But we already know what the integer is. It's itself. So next we have prove n divides n. Sounds a little bit harder. Except we kind of already proved that. So, again, we need some integer a inside, some integer a such that n is equal to n times a. Let a equal 1. If a equals 1, then we have n times a is equal to n times 1. But that is just n, as previously shown. Alright, furthermore, let's go. Okay. Here's a good one. Prove. Alright, let me get my paper set up right to where you guys can see what I'm writing. Okay, it says prove that if m divides n, then m divides negative n. Alright. So, again, we start with what we know. So we're going to suppose that m divides n. If m divides n, then by definition, there is some integer a such that n equals m times a. So what we want to show is that there's some integer, let's just say, so we're trying to say negative n, m divides negative n. Then there's some integer b, this is, what to show. Like what we want to have through this definition. So we want to show that there's some integer b such that negative n is equal to m times b. So let's see. I think for this, okay, this shouldn't be that difficult either. I'm thinking all we do is, we're going back to what we know. We know that m divides n, so n is equal to ma. So let's multiply this by negative 1. It's just an equation. We can do that as long as we keep both sides balanced. And then we have, n equal to ma is equivalent to n is negative m a. Well, then this should be equal to negative n times m negative a. Through associativity, I can move I'm actually not sure if that's right. Like, I know we're on the right track. I just don't know if it's associativity that allows me to move this. What would this be if I well, yeah, that would just be the negative of MA. Yeah. Okay. Yeah, I would multiply the integers together first. Because otherwise it would just be putting a positive there. Because it'd be negative, negative. So yeah, we wouldn't distribute it. So negative n is equal to negative ma. So I shouldn't have put the parentheses there at all. This should have just been negative ma. But then we could just say that is m negative a. But then that means that there's an integer negative a. So then from there we can just say negative a is an integer. Since a was an integer, the negative is also an integer. And this right here shows that m divides negative n. Okay. Let's see.